Hello, am I audible?
Yes, ma'am.
Yeah, so we will wait for 5 more minutes and then we'll start.
Sure, ma'am.
So today we will revise whatever theory is covered in week 12, that is ordinary differential equations. So there are mainly two equations which we are going to learn. So first is the linear ordinary differential equation, and second is the another ordinary differential equations with higher power. But in that case, our our particular focus will be on homogeneous ordinary differential equations. Okay, so let's wait for 5 more minutes if someone will join, and then we'll start.
Ma'am,
Yes,
I wanted to say that I am not joined in discourse. So how will I join it?
you don't have your discourse ID.
No, ma'am. I am
Okay,
joined in a discussion form, but when I post any question, we don't get any reply there.
okay. So have you mailed this recording support team?
I thought to ask in class today.
Okay, actually, I don't have any information about this, that how you guys will get the discourse ID. If someone has discourse ID, so can you guys guide her, Rajdeep or Chetan? If you guys know about discourse ID or you have discourse ID or not, can you share something? So Chetan is here. Chetan, am I audible to you? Student.
Yeah, ma'am, you are audible.
Yeah, so do you have discourse ID?
Yeah, I'm joined in this course, ma'am.
Through your student ID only.
Yeah, student ID only, ma'am. I got a mail and then I register for it.
Okay. So Ananya, please check your mail. Although I'll share this problem with sir, he will ask to the support team that what if something is happened wrong from our side. But once just go through your inbox if you have any mail regarding discourse or something.
Ma'am, by the way, we didn't got a student ID till now.
Okay. Okay, fine. I'll let you know what is the case.
Okay, ma'am. Sure, ma'am. Thank you, ma'am.
Okay, so let's start. Yeah, I'll inform sir about this issue and let you know what is the procedure. Okay, so let's start from introduction to differential equation. So actually what happened when we perform some experiment or we do some physical work, so there you observe that at the end, the problem actually reduced to solving some kind of an equation. Okay. So so there are most of the physical problems. So many physical problems, physical world or real world problem actually reduces to solving an equation. Solving an equation. Okay. So now here we are talking about a specific case of equation. In that equation, we have a function of x. So in this equation, we have some function of x and its derivatives too. And its derivatives. So such kind of equation is known to be a differential equation. And what is this ordinary word means? So since we haven't introduces the partial derivatives, so whenever there is only simple derivative, so that means here the function is actually only one variable function. Okay, so about this one variable, two variable, these things you will learn in the further courses. So if you have a one variable function, so that means if a function is if a function is can be expressed using a single variable x, then that function will be a function of one variable. And if an equation involve a function with its derivative, then such kind of an equation is known to be an ordinary differential equation. Okay, so here this word ordinary, is actually indicate that our function is of one variable. Differential means it includes its derivative. And equation, so equation means we have some kind of relation which express the connection between all these terms. So that's why we call it an ordinary differential equation. Now any ordinary differential equation actually categorized by the highest power of derivative is present there. So that means if we have an ordinary differential equation in which we just have a single derivative means, so let's suppose, so the categories or the categories of ordinary differential equation, we briefly introduced that ODEs to be ordinary differential equation is actually based on the highest derivative present in the equation. Okay, so that means whatever highest derivative is there, we actually categorize our ODEs into those categories. So that means if we have only single derivative, that means first derivative of any function, then that will be our linear ordinary differential equation. And if we have a second derivative in our equation, that will be our second order ordinary differential equation. And that is usually known as to be an order of ordinary differential equation. Now, with a specific power, we have several methods to solve the ordinary differential equation. So we'll start with looking by the linear ordinary differential equations and then go to the much more higher power of ordinary differential equation and learn how to solve such kind of an equation. But in our course, we mainly talk about linear and quadratic. So that means it will have either only one derivative or the first derivative of function, or it will include the second derivative of function too. Okay, so we will learn these two ordinary differential equation and how we can solve such kind of differential equations. Okay, so this is a basic introduction. Again, I'll repeat that the categories of ordinary differential equation is based on the power of derivative or the power of what will be the highest power of derivative we have. Okay, so if an ordinary differential equation includes only function, so that means f of x and f dash of x with some combination of function of x with other functions of x. Then that is known to be a linear ordinary differential equation. And why it's known to be a linear? Because here we just have a first derivative f dash of x. So here the power is 1, so that's where the word linear comes. So the linear ordinary differential equation means an ordinary differential equation in which we have only first derivative. So we can take some example of such kind of an equation. So suppose we have an equation something like this. Let's take any function. So that is f dash of x plus x square f of x plus is equals to x cube, we can say. So this is one example of ordinary differential equation. So here in place of f of x, you can take any function that will create us an ordinary differential equation. We also have some kind of equation like sin x f dash of x plus cos x f of x minus 10x is equals to 6 square x. Okay, so this is also one kind of ordinary linear ordinary differential equation. So here you observe that we have a function f, and it just and this equation involves just only first derivative of that function. That means f dash of x. So such kind of an equation is known to be a linear ordinary differential equation. So first we will learn how to solve such kind of ordinary differential equations. Okay, is there any doubt so far? Okay, so if you don't have any doubts, or in between if you got any doubt, you can interrupt me and we can discuss. Okay, it's not an issue. And if the speed is too much, then also you can tell to. I'll just slow it down. Okay, so these are the two ordinary differential equations. These are the two particular examples of ordinary differential equation. So now we will first what we do, we introduce some sort of general form to write such kind of ordinary differential equations. Okay, so here you observe that here in place of f dash of x, if we have any function, then what we can do, we can just divide by that function and make the coefficient to be equal to 1. Okay, so this is the case we can always do. So that's why the standard form, so the standard form of any linear ordinary differential equation is this form. So that means here we have f dash of x and plus p of x f of x is equals to q of x. Again, the reason is simple why we are taking 1 here, because we know if there is any function here, then we can just divide the whole equation by that function and make a coefficient of f dash of x to be equal to 1. So that's why in general, whenever we talk about linear ordinary differential equation, this will be our standard. Okay. Now we will learn how to solve ordinary differential equation using a standard. So in the standard, because if we know the solution for any standard form, then we can have a solution for any particular type of ordinary differential equation. We just have to put the values of px and qx and solve the integration or differentiation, whatever involved in the process. Okay, so let's start how to find out the solution of linear ordinary differential equation. Solution of linear ordinary differential equations. Okay, so here the solution, so we categorize the solution into two parts. So the cases are two. So the cases are two. So in the first case, what we do? So in the first case, we treat p of x to be a constant function. So that means p of x. So these categories or these cases are made by the choice of the function p of x. So the first choice is when p of x is equals to p, a constant number. So here p is a constant, and another category is when p of x is any function of x. So you can say that the first one is nothing but a particular case of the second one, because here a constant function is also can be treated as function of x, even though it doesn't depend on x, but we can say that it's a function which maps all the input value to one particular one. So we can say that it is also a function of x. So you can say that this case is actually a particular case of a particular case or particular scenario of case 2. Okay, so let's start with when p of x is just a constant. Okay, so in that case, how our linear differential equation will look. So we know that the standard form is this form, so which is f dash of x plus p of x into f of x is equals to q of x. So here in place of p of x, we have to take a constant value. So let's and that value is denoted by simple p. So here in the first case, so in the case number 1, our standard form will be f dash of x plus p of f of x is equals to q of x. Now in this case, we have to find a function which can satisfy this kind of linear ordinary differential equation. So that is the meaning of getting a solution for linear ordinary differential equation. So ultimately, we need a function f of x which actually satisfies such kind of condition. Okay. So here we observe that here we have f dash of x, and here we have some constant multiple of f of x. So we can some kind of think a function by which we can reduce this addition into a one term. Okay. So what we want to do? So we want to compress this left hand side into one function in such a way that if we take the derivative of this function, it will become the left hand side. Because if we do that, then we can simply integrate into both of the sides, and this side will get much simpler in terms of f of x. It won't involve any derivative of f dash. Okay, so that's our main purpose to main motive. How can we find a solution of this equation? Okay, so ultimately we want to think about a method or think about some kind of adjustment which reduce our problem for into the only solution of an integration, and that means the only thing we need to do is just an integration. Okay, so for here we have one familiar kind of function which is nothing but the exponential function. So here you observe that if we take some kind of if we take this function, that e to the power p of x so if we take this function, so e to the power of p f dash of x plus p e to the power p of f of x is equals to q of x, right? E to the power p q of x we can say. And here if we try to reduce it, then also this e to the power p is nothing but just a constant. So it will give us some simpler kind of form. Okay. So first we try to deal with the function p of x, and then we come to e to the power p, because here it's just a particular case. So suppose in place of p, if we have some kind of a function, so let's take it p of x, then what will be the solution? So that means suppose our form is now f dash of x plus p of x f of x is equals to q of x. So what we do, again, we want to reduce this function in such a way that we just get one function whose derivative is another type of function. Okay. So for that, what we do, we just multiply by a function in this way. So here the function will be, so here, so we multiply by the factor e to the power integration of p of x d of x. Okay, so this is the general factor, and this is also known as an integration factor. So if you multiply by this factor into our equation, then we will get some simpler form. So let's try to multiply with this factor, and let's see what is the simpler form we are getting. So here it will be e to the power integration of p of x dx into f dash of x, and then plus p of x e to the power integration of p of x dx f of x, and this is equal to e to the power integration of p of x dx into q of x. Right. So here we can reduce this left hand side with some simpler kind of integration, and which is nothing but the derivative of e to the power integration of p of x dx f of x, and the whole derivative, and this will be equal to this function, which is e to the power integration of p of x dx into qx. Okay, now the problem reduces into integration only, because if we take the integration over the left hand side and right hand side, we'll get our solution. So here the solution will be e to the power integration of p of x dx f of x is equals to the whole integration of this particular term, that is e to the power integration of p of x dx into q of x dx. So now ultimately the whole scenario reduces to only simple integrations. So that's how we can find out the solution of any ordinary differential equations. Okay, so let's try to go to the second order linear differential equation, and then we can discuss some of the activity and practice assignment problems. Okay, so this is the general form. So ultimately, what is our conclusion? So our result will become, if we have a linear ordinary differential equation in this form, which is f dash of x plus p of x f of x is equals to q of x, then the solution of this linear differential equation, linear ordinary differential equation, is simply this function, e to the power integration of p of x dx into f of x is equals to integration of e to the power integration of p of x dx into q of x dx. Okay, so ultimately, this is the conclusion we have made. That if any linear ordinary differential equation we have, we can eventually find out the solution of that linear ordinary differential equation. And that is nothing but equal to this particular equation. Here we just have to solve the integrals and we'll get our solution. Okay. Now let's go to the second order differential equation. So as the name suggested, we have second order differential equation. So that means these second order linear differential equation. Linear differential equation. So here these equation also known as first order linear differential equation. This is first order linear ordinary differential equation. The first order actually reflects the power, and here the linearity actually represents the power of this f dash of x. Okay, so here the power of f dash of x is 1. That's why the word linear, sorry, my bad, I have told earlier a little different. But here actually it is known as the first order linear ordinary differential equation. So here the first order tell us that the derivative has order 1. So that means we have f dash of x. And the linear actually tell us that the power of the derivative and the power of the function, both things are actually equal to 1. Or we can just simply say that the power of highest derivative is equal to 1. So that's why it's a first order linear ordinary differential equation. Now what will be the second order linear differential equation, ordinary differential equation? So here this second order suggests us that the equation will have f double dash of x. And the linear suggests us that the all powers of powers are of degree 1, right? Or all powers are 1. All powers of f of x and f double dash of x are 1. All powers of f of x and f dash of x and f double dash of x are 1. Okay, and ordinary differential equation, again, since we have a function with one variable, that's why the word ordinary differential equation. So in general, what will be the general form of second order ordinary differential equation? So the general form is actually something like this. Again, we can treat f double dash, again, we can treat the coefficient of f double dash of x to be equal to 1. So we have f double dash of x plus some p of x f dash of x plus some q of x f of x and is equals to some r of x. This is the general form or the standard form for second order linear ordinary differential equation. In our course, we try to find out the solution of a very specific case of this second order ordinary differential equation. That case is when our function p of x, q of x, r of x, all are constants. Or we can say not r of x, we can say p of x and q of x, all are actually constants. So such kind of ordinary differential equation are those which we want to learn, and also the solution of such kind of ordinary differential equation. But again, we actually characterize these differential equation into another two parts. So what are these two parts? So these two parts now characterized by the choice of r of x. So that means if we have r of x to be equal to 0, that means over the right hand side, if we just have a 0, then it will be known as the homogeneous ordinary differential equation. Homogeneous ordinary differential equations. And if this r of x is not equal to 0, then those equations are known to be non-homogeneous ordinary differential equations. So again, based on the right hand side value, we characterize our ordinary differential equations into another two cases, and those are homogeneous ordinary differential equations. So when our r of x is equals to 0, and non-homogeneous ordinary differential equation when r of x is not equal to 0. Okay, so now in our course, we have a specific type of second order ordinary differential equation, which is second order of ordinary differential equation with constant coefficients. Okay, so second order linear ordinary differential equations with constant coefficient. So as the name suggested, all the coefficient of f of x, f dash of x, and f double dash of x will be constants. Okay, so with the constants coefficient. Coefficients. So now again, what will be the general form here? So the general form will be, we can take a f double dash of x plus b f dash of x plus c f of x plus c f of x is equals to qx. So this is known to be the second order linear ordinary differential equation with constant coefficient. Again, the second order denoted that we have the second derivative of f of the function f of x, which is f double dash of x. The word linear suggests us that all the power of f double dash of x and f dash of x as well as f of x is nothing but equal to 1. An ordered differential equation, because our function is just of one variable, that's why ordered differential equation. And again, constant coefficient means all the coefficient of these functions are nothing but the constants. So such kind of differential equations are second order linear ordered differential equation. So we will. So Ananya, actually, I asked sir about your discourse ID. So he said that you will get discourse ID after one term. If you complete your one term, then you will get your discourse.
Okay, ma'am. Thank you, ma'am.
Now let's try to understand how we can find out the solution of such kind of ordinary differential equation. So again, we characterize our second order ordinary differential equation constant coefficient into two cases. So the case one will be when q of x is equals to 0. So that means the homogeneous one. And another one will be when q of x is not equal to 0. Right? That means the non-homogeneous one. So these are the homogeneous and these are the non-homogeneous. So in our course, we particularly understand how we can find out the solution of homogeneous ordinary differential equations. Okay. So now again, we try to guess some function which actually reduces our right hand side or left hand side with much more simpler type of equation. So that means at the end we just have to find out some integration or something else. Okay. So for that we have one method where we can get that the solution of our second order differential equation is nothing but e to the power some p of x or something, because exponential function is the only function which we can find out an a, b, and c in such a way that f of x is equals to that p of x will be a solution. So let's try to understand. So here, if we guess or if we assume that f of x is equals to e to the power cx is the solution, then what will be the case? Okay, so is it possible or not? So let's try to find out. So here, if f of x is equals to e to the power cx, then what will be the value of f dash of x? It's nothing but c e to the power cx, right? Just by the chain rule. The value of f double dash of x, it will be c into c e to the power cx, which is nothing but c square e to the power cx. Now let's try to substitute these value into our second order linear differential equation with constant coefficient. So then the equation will become a of c square of e to the power cx plus c of e to the power cx and plus a of plus b into c of e to the power cx and plus are we using c here? Okay, so we are using c here. So let's take another number. So let's take it to be p. Where p is any constant. So where p is any real number or complex number, whatever we can. B. So here we will get p square. So this will be p, this will be p into p, and this will be p square. Okay. I just change the whole thing from c to p because we are using c in this particular equation. So that's so it will be a into p square of e to the power px plus b into p into e to the power px and plus c into e to the power px, and this should be equal to 0 if we are talking about the homogeneous part. Okay, so in this case what will happen, we can take out e to the power px common from each of the terms. So ultimately it will reduces to a e to the power a into p square plus b into p plus c into p into e to the power px is equals to 0. Okay, so here it's not a function, it's just p into x, where p is a constant number. Okay, now here we know that the function e to the power px never takes the value 0. So here we know that e to the power px is actually not equal to 0 for any p. Right? So from that we can conclude that if you want to make this equation to be equal to 0, this term should be equal to 0. Right? So it will imply that a of p square plus b of p plus c of p should be equal to 0. And if this is equal to 0, we actually return to the quadratic equation where we need to find out the value of p for which the quadratic equation is equal to 0. So that means we want to find out the root of the quadratic equation. So we can calculate what is the what we can find out what is the value of p by just solving this equation, by just solving this equation. Right. So here we return to quadratic equations from our ordinary differential equation. So overall, from these all observations, we can make a results which actually tell us how we can find out the solution of second order differential equations with constant coefficients. And what is that result? So this result says that it actually based on the roots we are getting for this particular type of equation. So it says that if we have a homogeneous second order differential equation, which is a f dash of x plus b f of x plus b f dash of x plus c f of x is equals to 0, then from this equation we can make an quadratic equation by just taking by just replacing f dash by replacing f with some s. So that means ultimately we get some kind of equation like this, that a of p square or s square you can take. So a of s square plus b of s plus c is equals to 0. Okay. So ultimately the nature of the solution of second order differential equation reduces to the nature of this particular equation's root. Okay. So the case one. So we will take 3 cases in this also. So the case one is when this a square plus bs plus c is equals to 0 will have 2 distinct real roots. So if this equation will have 2 distinct real roots, then what happened? Then we will say that the solution is, and the solution of equation can be, so let's assume that these 2 roots are nothing but s1 and s2. So then the solution of equation can be e to the power s1 of x, or can be e to the power s1 of x and e to the power s2 of x. So that means you can take f of x to be either e to the power s1 of x or e to the power s2 of x. But observe that if we have 2 solutions for one ordinary differential equation, then what will be the other solutions for this particular differential equation? Okay, so suppose we have 2 functions which solve our ordinary differential equation. So suppose f1 of x and f2 of x are 2 functions, are 2 solutions of some ordinary differential equation. So let's take it a particular case. So suppose we have a ordinary differential equation with constant coefficients. So that means a f double dash of x plus b f dash of x plus c f of x is equals to d. Okay. So in this case, we are saying that f1 and f2 both are the solution. So that means both should satisfy this equation. So that means a f1 double dash of x plus b f1 dash of x plus c f1 of x is equals to d. This should be true, and similar thing should happen for f2 also. So that means a f2 double dash of x plus b f2 dash of x plus c f2 of x is equals to d. Now for finding the solution of this, now from these two equations, we can judge. Okay, so if f1 is a solution and f2 is also a solution, then if you take any linear combination of these two functions, so that means if you take another function g of x with this thing, that it is nothing but c1 of f1 of x and plus c2 of f2 of x, where c1 and c2 both are constants. Both are constants. So in that case, we can actually say that g of x is also a solution of our ordinary differential equation. How? Because we can compute g dash of x. So g dash of x is nothing but c1 f1 dash of x plus c2 f2 dash of x. Okay. And what will be g double dash of x? G double dash of x will be c1 f1 double dash of x plus c2 f2 double dash of x. So ultimately, if you substitute this g, x, g dash and g double dash in our equation, we will get that a of g double dash of x plus b of g dash of x plus c of g of x. This is nothing but actually equal to a of a into c1 of f1 double dash of x plus a into c1 of f2 double dash of x. Ultimately, we just reduces it into the f1 double dash equation and f2 double dash equation, and it will tell us that g of x will be our solution. Okay, so that's the thing we are computing. Plus b of again we have to substitute in place of g dash. We have to substitute this now, which is c1 f1 dash of x and c2. So here that should be c2 f2 dash of x. So it will be b of c1 f1 dash of x and then plus b of c2 f2 dash of x. Okay. And similarly, we can say plus c of c1 f1 of x and plus c of c2 f2 of x. So ultimately, you can say that this is nothing but c1, and here we have a f1 double dash of x. So that is a f1 double dash of x plus c1 b f1 dash of x plus b f1 dash of x, right? And plus c1 with c f1 of x. That means c f1 of x, okay. And which is plus c2 of the same thing with f2 double dash. Okay. So ultimately, we know that these two equations are solution, but here this won't work if we take non-homogeneous part. So that means if we take any d here, then it won't work. But in place of d, if we have 0, then we can say, because 0 plus 0 will become 0. So in place of d, if we have 0, then ultimately it will become nothing but c1 into 0 plus c2 into 0, which is equal to 0. So that means if f1 and f2 are the solution of a particular ordinary differential homogeneous second order differential equation, then their linear combination will also be a solution of the same equation. So ultimately the result will become, so thus we get if f1 of x and f2 of x both are the solutions, then their linear combination, which is c1 f1 of x plus c2 f2 of x, will be a solution. Okay, so this is the result we get. So let's go back to a second order ordinary differential equation. So here we observe that if this particular equation has two distinct roots, which are nothing but s1 and s2, then e to the power s1 and e to the power s2 both will be the solution. So ultimately we can say that if this equation as square plus bs plus c is equals to 0, will have two distinct real roots, then the solution of the particular ODE will be, so you can take f of x to be equal to c1 of e to the power s1 of x. Sorry, it's not a function, just s1 into x. So s1 of x and plus c2 e to the power s2 of x. Okay, so this is the one result we get. Now what happens if we don't have two distinct real roots? In case of two distinct real, we have two same roots, right? So suppose if this particular equation a square plus bs plus c is equals to 0 will have same roots. Let's name it to be s. Then what will be the solution? Then here we'll just get e to the power s of x plus c to e to the power s of x. It doesn't make sense there. So in this case, we just have a little bit change. So that change is in the second function, we just take x into e to the power s of x. Because here you observe that if this equation will have only one solution, which is s, then e to the power s of x and e to the x into e to the power s of x, both are the solutions. Both are the solutions. So ultimately, we can say that any linear combination of these two functions will be a solution. So thus f of x will be nothing but c1 of e to the power sx plus c2 of e to the power c2 of x into e to the power sx. So here the c1 and c2 actually depend on the nature of second order ordinary differential equation. So if you want to find out c1 and c2, there we have, if we there we need some additional conditions. We need some conditions on f dash of x and f of x for finding out the values of c1 and c2. It based on a particular question. So if we have some question in which we have some conditions on f dash and f of x, we can actually find out the values of c1 and c2. Okay. Now let's discuss the last case when we have the complex root. Okay. So in the complex root is same as the first one, but here we can change a little bit in complex root because we know that e to the power iota theta is nothing but cos theta plus iota sin theta. So we use that identity and try to form a nicer form for the solution. Okay. So now here the third case will occur. So if a s square plus bs plus c is equals to 0, we'll have complex roots. So if it is so if this equation is having complex roots, so it is only possible if the roots are in conjugate pair, right? So because the root of this equation will be of form that s is equals to minus b plus minus under the root of b square minus 4ac by 2. And if we need complex root, we need this particular term to be equal to be in negative, because then only we'll get complex roots. But also because of this plus and minus, we always get complex roots in pair of conjugate. So that means if one root is z, another root will be z bar, the conjugate of z. So because of this particular Sridharacharya formula, we always get complex roots in pair of conjugates. Right. Because this only factor will involve iota, and both roots are only dependent on only differ by the plus and minus sign. So we know that the plus and minus sign with respect to iota is differ in z and z bar. So here if the one root is alpha plus iota beta, another root will be alpha minus iota beta. So let's say that alpha plus iota beta and alpha minus iota beta are the roots. Then again, by the previous case, we get that e to the power alpha plus iota beta of x. Sorry. And alpha minus iota beta, e to the power alpha minus iota beta of x, both functions will be the solutions. Both are the solution. But we know if both functions are the solution, their linear combination will be a solution. So ultimately, the function f of x will become that c1 of e to the power alpha plus iota beta of x and plus c2 of e to the power alpha minus iota beta of x. Right. So here what we can do, we can just take common e to the power alpha, right? And we get some simpler form. So here it will become c1 e to the power alpha x and sorry, not c1, just e to the power alpha x. And in the bracket we have c1 e to the power iota beta of x and plus c2 e to the power minus iota beta of x. Okay. Now here we can use our general convention that if we have e to the power iota theta, this can be written as cos theta plus iota sin theta. Right. So in place of theta, we have beta of x. Okay. So that means, so let's say, thus we have that e to the power iota beta of x can be written as cos of beta of x plus iota sine of beta of x. And what will be e to the power minus iota beta of x? So it will be cos of minus iota minus of beta of x, which is same as cos of beta of x. And then plus, now here in place of iota, we'll get minus iota sine of beta of x. And we can substitute in this particular equation. And just by adjusting some of the constant, we conclude that the function f of x will look like e to the power alpha of x with some another constant. In place of c1 and c2, you'll get some another constant. And the only functions we have cos beta of x and sine beta of x. So we can say that the solution is nothing but in this form, that e to the power alpha x into sum of the constant c1 into cos of beta of x and plus c2 tilde and sine of beta of x. Okay. And this c1 and c2 are just some constant, some calculation away from c1 tilde and c2 tilde are just some calculation away from c1 and tilde. We just have to substitute these values and calculate what is the coefficient of cos beta of x, sine beta of x. So ultimately, with this, we can say if we have a complex root for our equation, then the solution will look like something like this. So at the end, we can make a table. So we say that if we have a, so first thing is we are talking about the roots or zeros of, or you can say roots of, or whatever you want to say, x-intercepts of a x square plus bs plus c is equals to 0. So if they are real and same, real and distinct, then the solution f of x is nothing but, so let's take it to be s1 and s2. c1 e to the power s1 of x plus c2 e to the power s2 of x. And this is our solution. Now, second thing is when the roots are real and same, let's name it to be s, then the solution is c1 e to the power sx plus c2 x e to the power sx. Okay. And the third case, when the roots are complex, let's name it to be alpha plus minus iota beta. So in that case, the solution will look like some e to the power alpha x will get common, some constant of c1 of e to the power beta x and plus c2 of e to the power, sorry, not e to the power, c1 cos beta x plus c2 sin beta x. Okay, so these are the solution we get if we try to solve the second order homogeneous linear differential equation. For non-homogeneous, we need much more work to do. And for non-homogeneous, we need another type of solutions too, which is known to be the particular solutions, which we'll discuss in another courses. But in this course, we just solve the constant coefficient homogeneous second order ordinary differential equation. Okay. So this is the basic theory of ordinary differential equation. The main purpose of our study is just to find out the solution of ordinary differential equation. Okay. And these are the two categories, linear and second order. In the second order also, we have homogeneous with constant coefficient. So for the linear, we have a very nice formula for solving it. Right? So for solution of linear ordinary differential equation, we just need to apply this particular form, right? And do the integration. That will be our solution. And for the second order homogeneous part, we have three points, which actually depends on the nature of this particular equation. A square plus bs plus c is equals to 0. And because of these three forms, we can find out the solution for second order too. Okay. So that's the theory from week 12. Now, there are some particular equations which were discussed in the lectures. Those equations are equations for AC circuits. Right? There are some LRC series circuit with AC sources, with DC sources, and some LC oscillators. Those equations are discussed in the lectures and explain the solution of such kind of an equation. Okay. So let's go to the activity. So if you guys have any doubt from the activity, you can ask now. Just mention the activity number and question number, and we can discuss the solution. Is there any doubt? Ananya, is there any doubt from your side?
I didn't got any doubt in there.
Okay. So, or anything, any else, any other topic you want to discuss? That's also fine. You have any doubt in general in maths, you can ask. Okay. So, Rajdeep, do you have any doubt in week 12 activity practice assignment?
No, ma'am.
Any other doubt?
No.
Chetan, do you have any doubt? Anything you want to discuss?
Ma'am, important topic of INSEM.
Yeah, so we will tell all the important topics and the mark distribution in the revision session. Okay. So I haven't prepared the mark distribution yet. So I'll also have to ask. So in the revision session, we will discuss it in detail. So what is the major portion will be from after week 8, right? Because we already in quiz 1 and quiz 2 we asked so many questions from week 1 to 8. So the major part of major portion of the question paper you can assume will be from week 8 to 12. So you can say that 80% question paper will be from 8 to 12. There will be mostly 2 or 3 questions from 1 to 8. Okay.
What is the weightage of end term exam for final score?
So we follow some formula. So I think in your student handbook or guide, they have mentioned some formula for calculating the end term score. So one of the formula, I am not sure that this formula is used or not. So in your student handbook, you will find out some formula which will give you the end term score. Or total score overall. Okay. So the total score. So it is something like 0.1 of your GA. So that means whatever GA you will get, you'll add 0.1, and then there will be some maximum of. Here we have some distribution. So in
Quiz
some,
1 and quiz 2.
so you can find out this formula in your student handbook. So they follow such kind of formula for calculating the total score of your course. I don't actually precisely remember. There is some involvement of quiz 2, quiz 1, and final exam. So one part I think I know, which is something like the size that 0.4 of final exam and plus 0.3 of quiz 2 and plus 0.1 of quiz 1. Something like this. I'm not sure about this formula, but there is some formula by which we can evaluate the totals. Okay. So here from this formula, you can assume that what is the weightage of final exam. Okay. So one thing I can say, it will be more than the quiz 1 and quiz, more or less, a little bit more from quiz 1 and quiz 2 maybe.
Can you solve the question number 4th of graded assignment 11?
Yeah. Graded assignment 11, right? Question number 4, right?
Yes, ma'am.
So this is the integration, right? You have given I is equals to minus a to a. This one, am I right? Ananya, is this the question?
Yes, ma'am. Yes, ma'am.
Okay.
I1 is equals to root a minus x, something like that.
Yeah, fine. So here what you have to do, so the hint is given that we have to use the property of integration, that 0 to a f of x dx is equals to 0 to a f of minus of x dx. Okay. So from that, if you calculate I1, it will reduce into some simpler form. So let's see what is the I1 minus a to a. So I1 is integration of minus a to a under the root of a minus x into a plus x dx. Okay. So here we have one property, that integration minus a to a 0 to a is same as actually here we have to use some another property. It's not same as this one.
I used the substitution one.
You use the substitution by cos or sin? Something
Yes,
like
ma'am. It was, I think, a cos theta or maybe a sin theta.
that. So x is equals to a cos theta. So let's take it cos theta. So minus a to a is this. So okay, so it will reduces to pi and minus pi. Right? Because when a is equals to when x is equals to a, it will become cos theta is equals to 1. So that theta is actually equal to for 1 we can take pi. Oh, sorry, pi is for minus 1, right? So for 1 we can take 0. And when theta is equals to minus a, the cos theta will be equal to minus 1. So sorry, when x is equals to minus a, cos theta will be equal to minus 1. So that means theta is actually equal to pi. So we can take the limits will be from pi to 0. And it will become under the root of a minus x. So that will be a minus a cos x upon a plus a sin x. And in place of sin theta, sorry. In place of dx, we need some kind of d theta. So here dx will become a. The derivative of cos theta will become minus of sin theta, d theta. So it will become minus of sin theta, d theta. So have you got the answer from this substitution? It will become 0 to pi. Now here is the issue. We can take a common and cancel it out. So it will become under the root of 1 minus cos theta upon 1 plus cos theta. This will be also cos theta into sin theta d theta. So here what we can do, we can try some another kind of substitution too. So which one of the thing I think we can do is just take this to be equal to t, because we have sin theta d theta here. So if we take t is equals to 1 plus cos theta, so it will become dt is actually equal to, the derivative of 1 will become 0. The derivative of cos theta will become minus sin theta d theta. Right. So here it will become integration 0 to pi under the root of, in the denominator we have t. So if t is equals to 1 plus cos theta, then what will be the value of minus cos theta? So you can take minus cos theta is actually equal to 1 minus t. That means 1 minus cos theta will be actually equal to 2 minus t, right? Because 1 minus 1 minus t. Oh, sorry. Yeah, I think I'm right. So it is 1 plus 1 minus t. So it is nothing but 2 minus t. So in the numerator, we'll get 2 minus t. In the denominator, we have t. And sin theta d theta will become only dt. And this minus sign, we have to adjust some here. So let's take it minus. And also we have to change the limit too. So here, if you take theta is equals to 0, it will t is equals to 1, right? When theta is equals to 0. And t will be equal to 0 when theta is equals to pi. Right? Because cos theta is minus, cos pi is minus 1. So t will be equal to 0. And because of this sign, we can interchange the limit from 0 to 1. The limit will be from 0 to 1 under the root of 2 minus t upon t into dt. Now it is a little bit simpler, but still we don't have exact form. So you can say that this is same as 2 by t and minus of 1 dt. So for this form also we need some another kind of substitution. So I don't think the substitution actually works here. We have to use some of the properties.
By the way, I think we can put 1 plus cos x or maybe 1 minus cos x as sine 2 sine square x by 2.
Yeah, we can do that. 1 plus cos x as
Will not work also. By that formula, cos 2x is equals to 1 minus 2 sine square x.
okay.
So minus cos x will be equal to 2 sine square x by 2.
are you getting the solution from that particular substitution?
That's why I reading.
Yeah, so I think it's actually based on some property of integration. So let's use some another property. So that property we know one property also, right? Integration minus a to a f of x dx. This is actually same as integration minus a to a f of minus x dx. And why this property holds? Because in place of x, if you take minus x, if you take x is equals to minus of x, then dx will become minus of dt. And this, dx will become minus of dx. And this minus sign will get adjusted by the limit. So that's why this property holds. So I think we have to use this property. They have given some wrong hint or maybe. So let's try to use this property. Okay. So here the I1 is integration minus a to a f of x dx, which is actually equal to a minus a to a under the root of a minus x upon a plus x dx. So this is same as integration minus a to a. In place of x, we are taking a minus x. In place of x, we are taking minus of x. So it will become a plus x upon a minus x dx. Okay. So now we can use 2 iota. So now 2 I, because this is also equal to I, this expression is also equal to I, this expression is also equal to I. So 2I will become integration minus a to a of under the root of a plus x upon a minus x and plus under the root of a minus x into a plus x and the whole dx. Now here we can use some substitution so that we can get some simpler form of integration, which we already know. Okay, so integration minus a to a. So this is the whole under the root we can take here, and it will be our LCM of a minus x into a plus x. And here it will become a plus x the whole square, and then plus of a minus x the whole square, and then dx. So if we try to solve this, yes, Ananya. Is there any issue?
It's like this.
Okay, so let's see it. So this is integration minus a to a. It will become under the root of a square plus x square plus 2ax and plus a square plus x square minus 2x. And upon we have a square minus x square dx. So we're getting ultimately the same thing. Let's see. Minus a to a. This will be under the root of 2 times of a square plus x square and upon a square minus x square dx. So yes, ultimately we reach at the little more complicated form. Can we apply some substitution here? So let's see. So this is same as integration minus a to a under the root of 2 times 1 plus x square x by a the whole square and then 1 minus x by a the whole square dx. And then try to do the substitutions. So, but I think we reached the same point as we reached from here. Okay.
By the way, I think that we won't do in that in like we will solve it like a root then a plus x to the power whole square plus root a minus x to the power a whole square and then root.
Okay. You are saying that we can distribute this root over this step. Is that the thing?
Like as you distributed the root, I think we can do this in like in this. How will I explain? Like we will write this as a root a plus x upon root a minus x plus root a minus x
Okay, okay,
upon
okay.
root
Okay.
a plus
Yeah, yeah,
x.
I got it, got it, got it. Thank you. Yeah, so this is the then we will get the simpler form, right? Yes, thank you. So this is root
Yes,
of
ma'am.
a minus x upon root of a plus x, and then plus of root of a plus x into root of a minus x. Yes, then we get the simple dx. This is minus a to a, and this is the now it will become under the root of a square minus x square, and it will become a plus x. Sorry, it will become a minus x because the square root will get cancelled out, and then plus a plus x dx. So this will be equal to 2i minus a to a. This is 2a dx under the root of a square minus x square. So again, 2 into cancel out. I will be equal to integration minus a to a dx upon under the root of a square minus x square. And we can solve this using some
Yes, ma'am.
right?
Sine inverse x by a.
Right. Sin inverse x square. Right. Thank you for that.
And ma'am, that a will be in multiple.
Yeah, a times sin inverse of x plus c. Now there is one more integration, which is I2. Is there any issue in I2? I2 is simply
I
x
can
upon.
solve that one.
Yeah.
It was easy.
Right. It is actually easier than this. Just have to use the given property.
Thank you, ma'am. Ma'am, will you provide this later, this PDF?
Yeah, I'll upload it into the calendar. I think I haven't uploaded the last one, so I'll upload all the.
But when you upload it there, we will whenever we like to access it, it shows access denied.
Okay, so I think I haven't given the permission. This time I'll recheck it, and I'll try to open with some another email ID and check is it available to everyone.
Okay, sure, ma'am. Thank you, ma'am.
Thank you for joining. Is there any other doubt we can discuss, or else you guys can leave? That's all from my side.
Okay, thank you, ma'am. Good night.
Good night. Thank you.